Hello everyone, this is lesson 11 from our quadratics unit, the second part of completing the square. In our previous video, we looked at the introduction of the completing the square method and how it can be used to find the x-intercepts of any quadratic. We started with ones in which they were factorable. And as a good way to learn it, we used ones that were factorable so the solutions came out nice, whole numbers. But one of the things, very often expressions such as this, if I were to write down x squared plus 8x plus 7 equals 0, let's say we had that expression. We can use completing the square on that, but factoring is faster, right? And we would say x plus 7 times x plus 1 equals 0, and we get answers of -7 and -1. However, not every problem is factorable. And for instance, if we were to change just one of those numbers, let's say we had x squared, let's see, plus 8x, and we were to say minus, let's say 11 equals 0. That expression is not factorable, but completing the square will still work. And the x-intercepts that you get from that will not be whole numbers. They'll be decimals and involve square roots. And so here we're going to look a little bit more into some harder problems with completing the square, where you have expressions that necessarily aren't the easiest to factor or just they don't factor at all. So let's start with a bit of a warm-up, shall we? Some mental math. If I have x plus x equals 1/4, what should x be? Well, x plus x is 2x, so we're divide by 2. Here's a trick. If you need to divide a number by 2 and it's a fraction, an easy way is to multiply the denominator by 2. X equals 1/8. So next one, what if I had 3/2 squared? Well, what is 3/2 squared? Remember, when you square a fraction, multiply the numerator, multiply the denominator, that's x equals 9/4. Okay, 3/5 plus x equals 9/5. What happens here? Let's see, 3 plus 6 is 9, so x must be 6/5. And for the last one, 1/12 plus x equals 1/4. Not a common denominator, but 1/4 can be written as 3/12, and 1/12 plus 2/12 is 3/12, so x must be 2/12. You could also write that as 1/6. But the 6 wouldn't be clear from the 12 and the 4, certainly. What is clear, though, is that it does equal 2/12. Sometimes it's useful to keep fractions unreduced, especially in cases of completing the square. Sometimes it can help. But here, generally, you do it either way. All right, let's now dive into some equations. So as I said before, some of these equations can be a little bit unwieldy to use factoring with. Like for this first one. I mean, you could say that, well, is x equal to 3 and x equal to -1? No, and that's because of the presence of the 5, right? This is not the zero product property in this case. So our real only help here is to actually distribute this out. So we have x squared minus 3x plus 1x minus 3 equals 5. Okay? Now I'm going to combine some like terms, and then I'm going to take the 3, and I'm going to move it to the right side. The reason why I'm going to do that is to leave the space to complete the square. So I'm going to have x squared minus 2x, and then I'm going to take this 3 and I'm going to add it to the 5 to produce 8. Okay. So now I ask you, what number completes the square? So easiest way, how do we complete the square? Take the middle number, divide it in half. That's -1. And then what's -1 squared? +1. So we add 1 to both sides. So this becomes x minus 1 squared. 9. Now let's continue from here, right? When we write to solve, from completing the square, it's a perfect square term, and there's only two numbers that when squared gives you 9. That's 3 and negative 3. So I will write this as x minus 1 equals 3, or x minus 1 equals negative 3. And then from there, I'll just add 1 in both equations. So I get x equals 4, or x equals negative 3 plus 1, negative 2. And that works. And you can go back and find that those numbers actually work. You get 1 times 5 equals 5, or negative 5 times negative 1 equals 5. Okay, excellent. Let's try a few more. What about this one? X squared plus 1/2 x equals 3 over 16. Okay, same process, right? We're not changing anything, making it any different. We just have to think about what it means to complete the square. So let's take that half, right? So when I go to write it as a perfect square, like here, I had a 2 on the first problem, and when I had the 2, I divided it by 2 to get 1. What about a half? What's a half divided by 2? Well, half of a half, remember, use the trick, multiply the denominator by 2, and I get 1/4. So this is going to produce a 1/4. Okay? And then 1/4, what's 1/4 squared? 1/16. So I'm going to add 1/16 to both sides. So this now factors as x plus 1/4 squared. And then what's 3/16 plus 1/16? That's 4/16, which is 1/4. Okay. Perfect. So now let's see where we can go from here. 2 equations, right? So we write 2 equations. X plus 1/4 equals, okay, what times what gets you a 4th? Oh, we just did that. Isn't that 1/2? Or plus 1/4 equals negative 1/2. At negative 12, ooh. Because 1/2 times 1/2 is 1/4, and so is negative 1/2 times negative 1/2. All right. So now we subtract 1/4 from both sides, and we get x equals 1/4, 1/2 minus 1/4, or we get 1/4, yeah, so 1/16, yep. And then my other one I'm going to get by subtracting 1/4, I get x equals negative 3/4. So that also works. And here's the thing, because you get integer, you get rational answers, answers that can be represented as fractions. That original expression, if you were to put the 3/16 on the other side, it would actually be factorable, but not factorable in a way that is easy to spot. Okay, same thing with the last one, right? So let's look at this last one. We have x squared plus 3x plus 8/4 equals 0. Okay, so we bring the 8/4 to the other side. X squared plus 3x is negative 8/4. Now you may wonder, why is it 8/4? Isn't that the same thing as 2? But like we said before, sometimes with completing the square, it can be helpful to have denominators multiples of 4 like this. All right, so what's half of 3? 3 halves. Again, with problems like this, fractions help. Half of 3 is 3 halves, because if you do 1.5, and then you have to square it, you may not know off the top of your head that 1.5 squared is 2.25. But 3 halves squared produces 9/4. And so we add 9/4 to both sides. And so I get x plus 3 halves squared equals 1/4. So the idea is figure out how to complete the square, add that number to both sides, and then we factor it as such. Okay, 2 equations. It's going to be the same similar thing as last time, because the square root of 1/4 is 1/2. And so we get x plus 3 halves equals 1/2 or x plus 3/2 equals negative 1/2. Okay, we subtract 3/2 from this side. 1 minus 3 is negative 2. So I get x equals negative 2/2, which is negative 1. Or I subtract 3/2 from this side, and I get negative 1 minus 3 is negative 4. Negative 4/2, negative 2. So in this case, x equals negative 1 or negative 2, and it works. So completing the square makes this a little bit easier. We're factoring, I guess, yeah, x squared plus 3x plus 2 would have factored a little bit easier, but you know what? Sometimes we have to learn these processes. Here's a good reason. Okay. So let's take a look at this equation here. X squared plus 6x plus 7 equals 0. At first, it looks like it might be factorable, right? So, but let's see, 7 times 1 gives you 7, but they add to give you 8. Ooh, maybe it's not factorable. And look what happens. We add 2 to both sides, okay? They do this process a little bit differently. Rather than subtracting the 7 from both sides, they subtracted the 7 and then added 9 to both sides. That's what we would do. They did that, and they kind of combined 2 steps there to do that. So what we might have done is x squared plus 6x plus blank equals negative 7. They then add 9 to both sides to complete the square, getting this equation here. Okay, now here's the problem. You get down to the last step here, and you get this 2, and 2 is not a perfect square. So what happens? Well, when we go to write 2 equations from that, we are going to actually get 2 potential roots. When you take the square root of a number that's not a perfect square, usually we just leave it in a radical. So in this case, we have a 2. We take the square root of it, and it ends up as a negative 2. Positive or negative square root of 2. So we're going to leave it in that particular form. Now, here's something else that we notice. When they subtract 3 from both sides, right, here and here, notice that they don't put it on the right side. They put it on the left. There's a very good reason for it, a very simple reason for that, and it's not because of mathematics. It's because of handwriting. Way back, hundreds of years ago, most all of this math was handwritten. And, you know, people sometimes had good handwriting, and some of these mathematicians didn't have very good handwriting. So many times, if they put a minus 3 on the end of the problem like this, if you don't draw the fraction bar, or sorry, the radical bar correctly, and you maybe extend it a little bit too far, it doesn't become exactly clear as to whether the negative 3 is outside the radical or inside the radical. And that would be a completely different result. So the essence here is that we intend to do the square root of 2 and then subtract 3. So to make sure that meaning is perfectly clear, we put whole numbers on the left side when we do numbers that have both a radical part and an integer part. So we have 2 solutions for this. Negative 3 plus root 2 and negative 3 minus root 2. And that's what this plus or minus sign means. This plus or minus says that it's 2 numbers. To treat this as if it were 2 separate numbers, once where the sign is considered positive and once where the sign is considered negative. So plus or minus always leads way to 2 possible results. Now, negative 3 plus root 2 is this answer over here. And you can verify with a calculator that is in fact correct. And negative 3 minus root 2 is this number. So the lovely part about completing the square is that it can uncover these roots that are not whole numbers. And that's really where its true power lies. So we'll have to do another practice one of this just so you see how the radical part works. It's really no different than what we do. It's just that we can't take the square root of some numbers and we leave it in a radical format. Okay. So let's try a few here. So x squared plus 4x plus 1 equals 0. Okay, can you find two numbers that add to 4 and multiply to 1? No, can't. But let's see. And then I'll show you something pretty cool. All right, so once we have this, let's say we do subtract the 1 from both sides. Okay, and we get x squared plus 4x plus blank equals negative 1. Okay, let's complete the square. What number fills in the blank? Half of 4 is 2. So we know that's going to turn into x plus 2 squared. What's 2 squared? 4. Negative 1 plus 4 is 3. Okay, so now let's take this and let's actually come up with the two answers, right? You're going to write two equations. Now, you have kind of a choice with this. You can write this as a single equation, or you can write this as two equations. If you write this as one equation, what's going to happen is you're going to have x plus 2 equals plus or minus the square root. And the plus or minus sign, again, is what gives you the two different answers. One where it's a positive root 3, and then one where it's a negative root 3. Again, stemming from the fact that negative times negative is also positive. Okay. When I subtract 2 from the equation, I get negative 2. Oops. And then I do x equals negative 2 plus or minus the square root. Okay. Now, let's actually figure out what those answers are, right? So in a calculator, I'm going to go ahead and do a calculator. And so let me pull that up. Give it a second. Okay, so here's my calculator. All right, there's my calculator. So let's see what's happening here. If I were to do negative 2 plus, now the square root button, second and square root. Most calculators, the square root is like a second function of the x squared key. So negative 2 plus root 3, I get negative 0.268. So let's call it that. So let's say negative 0.268. So negative 0.268. And then let's do the other one. Let's do negative 2 minus square root of 3. And we're going to get negative 3.732. Okay, so those are going to be the two answers that we get from this. Now, if I can draw this on Desmos, I would find that those two would be essentially correct. But watch what happens, and this is going to be the pretty fun part here. So one of the questions that happens is like when we go back to factoring, right? Remember, factoring was always a case of what adds to the middle number and what multiplies to the end number, right? But does that work for problems that don't normally factor? Let's see. What happens when I add these together? I get negative 3.732, negative 3.732. Oops, let's do, yep, 0.732. Ooh, okay, 3, 2, a little bit of a lag here, plus negative 0.268, and I do get negative 4. Now, you may think, hey, shouldn't that be a positive 4? Don't forget that x-intercepts are always opposite sign from the factors, so they do add to 4 when you put them in factors. And do they multiply? Let's bring the calculation back. And let's take these two numbers and let's multiply them together. And you are going to get approximately 1, give or take the rounding. So guess what? Those are the two numbers that would add to 4 and multiply to 1. So they do exist, but they're in decimal form. Fascinating, isn't it? All right. Let's just do the second one as well. And let's see what we can do. Same idea, right? Let's move the 18. And so I have x squared minus 10x plus blank equals negative 18. What number fills in the blank here? Half of 10. 5 squared is 25. So I'm going to add 25 to both sides. And so let's see, what's negative 18 plus 25? That is going to be 7. And so now, again, 7's not a perfect square, but that's all right. I take the square root of both sides, and I get x minus 5 equals root 7, or x minus 5 equals negative root 7. You want to use a plus or minus sign on that? You certainly can. And so you add 5 to both sides, and you get x equals 5 plus or minus square root of 7. And if you want, you can do that to create the two numbers by doing 5 plus root 7 or 5 minus root 7. Okay. Same thing would happen even for number 3. Even this one, a little bit more messy because of the fraction, but hey, why not? Let's give it a try, right? So here we're going to move the 1/4 to the other side. So x squared plus 5x equals negative 1/4. Okay, so 5, half of 5, 5 over 2, 2.5. So it's going to be x plus 5.2, 5 over 2 squared. Now, 5 over 2 squared is 25 over 4. So we are going to add 25 over 4 both sides. Now, what is negative 1 plus 25? It is 24. And 24 over 4 is equal to 6. And now we solve from here. So again, 6 is not a perfect square, so I can just say x plus 5 halves equals plus or minus root 6. And so x equals negative 5 halves plus or minus square root of 6. Okay, and there we go. So that's how you would handle completing the square in all these different cases. Yes, none of these have x-intercepts that are whole numbers, but you can verify that these are in fact true through Desmos if you would like. Okay, so quick little summary here. Basically, completing the square always works as long as you find the right numbers and as long as you use things like common denominators or fractions that are not reduced. Okay, fractions help when squaring, as you can see for some of the expressions that we have here. They add 25 over 4 to both sides in this equation, and you get something that factors nicely. Okay, when you don't, biggest summary here, you don't have a perfect square, don't sweat it. Take the square root, show that it's a square root, stick a plus or minus on it to show that it's two possible roots. Okay, I think that's about it for here. Keep practicing those equations, and I will see you soon. Have fun, everyone.